Well, hopefully you recall that generators have all the same components as motors. Instead of converting electrical energy into mechanical energy, it's the opposite for a generator. You could grab the handle here and start cranking it, and the mechanical energy that you put in will result in some electrical energy output. But all the components are here. This purple line represents an axis of rotation, or an axle about which a loop of wire, we could call it an armature, is mounted and spins. Now, this might be the north pole of a magnet, and over here the south pole, so there's external magnets. And then we can see here, this part that's also mounted on the axle is the commutator. And the commutator is contacted by a pair of brushes. One brush touches that half of the commutator and another brush here on the back side. And so this is going to lead to the output of the generator. So how does it work? What governs the amount of voltage? Well, it all operates based off of Faraday's law, right? There's an induced EMF as the coil spins that's equal to negative N times the rate of change of flux. That means it's negative N times d dt of the vector dot product of B and A, which means the voltage you get output from a generator is equal to negative N times d dt of BA cosine theta. Well, the strength of the magnetic field doesn't vary, and the area of the armature doesn't vary. It's the angle between the two that varies as the axle is spun. So the EMF is equal to negative NBA times d dt of cosine, and here we'll say theta is omega t. If the axle spins at a steady angular speed, omega, then that value of omega is expressed in radians per second. And remind you that omega is d theta dt. Well, if it's constant, it's just theta divided by time. Okay, so we have EMF is negative NBA times d dt of cosine omega t. So the final result is that the EMF is equal to negative omega n BA sine omega t. If we were to graph this output voltage, it would look something like this. Well, it would just be a graph of negative sine. With a maximum value equal to positive omega NBA and a minimum value equal to negative omega NBA. Although it's pretty arbitrary when we set time t equal to 0. So for example, if the armature is in a horizontal plane when we start cranking the handle, then our graph of EMF versus time would look different than if the armature started out in a vertical plane. So this line represents the line t equals 0, but what's to stop us from shifting our origin in time to this point? Then we'd get a graph that says the EMF is equal to positive omega NBA cosine omega t, right? Because from here on, this just looks like a graph of cosine. So it doesn't really matter whether this is cosine omega t, sine omega t, negative cosine omega t, negative sine omega t. It could be any of those. We just say it's sinusoidal. We might pick one of these expressions as a matter of preference, maybe that one. In fact, there's no guarantee the origin and time has to sit at any special value. It doesn't have to be exactly when the output voltage is the most minimum. It doesn't have to be when the output voltage is a 0. It doesn't have to be at a maximum. We could have our origin and time at any random position, maybe here, where the EMF is instantaneously, who knows. So probably the best expression for the output voltage of the generator is omega NBA cosine omega t plus phi, where phi represents a phase angle that determines the difference between setting the time origin at such a point that the graph looks like cosine or setting the time origin at some other point, right? So we can just refer to that as, call a phase shift. And there you have it. It's important we review the behavior of generators because the rest of the focus on this Unit 5.2 on AC electricity is going to answer the question of what happens when we take electricity that comes from a generator and drive the resulting current through a combination of inductance, resistance, and capacitance. Much of our study is going to be dedicated to the LRC series circuit driven by the output of a generator.